Ever wonder what a watchdog timer is used for? Do you need one in your project? In this video, we will look at the watchdog timer provided by Particle and implement an even better timer using the underlying hardware of the NRF52840. And guess what? It is crazy simple. All right, well, let's jump into talking about watchdog timers. And of course, they're based on something called a watchdog. And this is a photo of my boxer called Argon, and he's going to be the model for being our watchdog in the context of this video. And he is not vicious, but we want to assume that our watchdog gets a little angry when it doesn't get petted. So first of all, let's talk about what watchdog timers are and what their purpose is. So first and foremost, we're really trying to protect against some type of malfunction in the software or potentially in the hardware that causes the device to stop working. And when this happens, what we want to do is detect that. And so watchdog timers are a perfect way to do that. And basically what they do is they trigger a system reset when a counter reaches a given timeout value. You can set this timeout value to really any value that you need. There are some range restrictions to it, and that will vary depending on the microcontroller you use. But you can make them, extremely tight down into the thousandth of a second, or you could be a couple days. And the watchdog timers are really important in safety critical systems, but they're also important in non-critical systems as well. For example, if we just take a thermostat that you might have in the wall, and let's say it hangs up for some reason, it just stops working. And at that point, what you have to do is pull the thing out of the wall or go find the circuit breaker, flip the circuit breaker, pull the batteries out. Essentially, what you're needing to do is to reset it. And when you reset it, 9 times out of 10, it will reset and start working normally again until something weird happens where it just hangs. And this is exactly what that watchdog timer is for. So when something like that happens and it hangs, it kicks off and does the reset for you. And on our NRF52840, the watchdog timer is clocked by its own dedicated real-time clock. That real-time clock is oscillating at 32.768 kilohertz. Okay? So let's first look at an implementation of the watchdog that you're going to find in the documentation for Particle. And I'm putting a little warning sign here because actually this is not what I would consider a true watchdog. This particular watchdog that's available in a very easy API to use will protect you from your own application hanging or not working properly. But it really is not going to protect you if the device OS were to hang or there would be some other critical issue with the software. And the reason that it's not going to protect you is because the watchdog itself is actually implemented in software. So there's a very high priority thread that's running all the time, and every time you check in, if you will, so essentially you declare the watchdog timer here. We've got application watchdog, which is the type. This is our variable. The 5,000 is 5,000 milliseconds, so every 5 seconds. And then this is the function that we want to run when the watchdog expires. And that typically a system reset. It doesn't have to be. It could be some other function that we provide. And then down in loop, here's the case where we're sort of going through this while loop, and we have some condition that causes us to stay in the while loop for a very long time. What we want to do is this wd.checkin every so often, at least shorter than every 5 seconds. And when we do that, the counter gets reset. It gets put back to 5 seconds, and it will start counting down again on its own. So we want to make sure we check in constantly. Now, if you don't do this here, every time loop iterates, it is doing a check-in for you. So you literally could just declare this, and then as long as you don't do anything for a long time and loop just runs continuously, those check-ins will happen for you. So again, this is one way to do a watchdog. It's a very easy way, but again, it's not being done by the hardware, and therefore I feel does leave you with some vulnerability in the fact that if the entire system stops working in some way, let's say that you have a memory leak and you start writing into memory that corrupts the device OS, and it basically goes into a hard fault condition, so it basically stops, but the processor's still alive. This watchdog timer is not going to help you. So we're going to look at the next level where we want to use the hardware capability built into the microcontroller for watchdogs, and that will protect us in many more cases. So if we look at the hardware watchdog steps, I've actually found that on this particular microcontroller, they're really easy. There's only 3 things you need to do and an optional 4th step if you choose to do it. And actually comparing this to like the STM32 microcontroller, setting up this watchdog is far easier than it was on the STM32 microcontrollers. It's also the case that you are going to run into a different methodology for doing this on every microcontroller family that you pick, and you just have to read the data sheets to see how to do it. So the standard is not very strict from an ARM Cortex standpoint. So the first thing that we want to do is there's actually 8 reload registers that are available to us. To do the watchdog that we want to do, we only need 1, and we just pick register 0 of that set of 8. The second thing we need to look at is how long do we want the watchdog timer to cycle down before it interrupts us. And so that time can be anywhere from 486 milliseconds down to 36 hours. So I don't know that I'd want anything that long, and this seems rather short. So we're going to just pick 5 seconds, and if things haven't fixed themselves within 5 seconds, it's going to reset us. Now the third thing that we want to set up, if we choose to do it, is the watchdog timer can be configured for 2 important things. One is, should the watchdog timer continue to tick down while we're in sleep mode? So if we go into a long sleep, then the watchdog timer may or may not still want to be running. And in that case, we have to decide whether we're willing to turn it off during a long sleep process. My view is that it's good to have it running during sleep, and you just set the watchdog timer value to a much higher value for the amount of time you're sleeping, so that you're ensuring that you're waking up and petting the watchdog every time. Now the other one, another key element of this is debug. So if you have the watchdog timer on and you hit a breakpoint in the debugger, if you haven't set this in the configuration register, all of a sudden you're going to get reset because you hit this breakpoint and you've stopped petting the watchdog. So what's really cool about this is you can set the watchdog timer so that it pauses when you hit a breakpoint. And I think that's a really cool feature. But you do have to set that in the configuration register. And then finally, you just start the watchdog timer. So once you've done that, you're off and running. So let's look at the registers. So I've jumped into the data sheet here and I've pulled out the key points for the watchdog registers themselves. So all the registers in the microcontroller are all mapped as though they're memory locations. So this is a memory location that is actually a register. And so this is where they've started the watchdog timer. And the actual task start, which actually triggers the watchdog timer, starts it up. This is the register that we're writing to. So it has this base value, and then we have an offset. And then there's a bunch of registers here that we can interact with, such as disabling interrupts. We can check the run status, is the watchdog timer running or not, and we can set up our various configuration load values, so how much are we going to reload the value for it to tick down and so forth. So the first one is actually this counter reload value. So this is the critical one where we want to set a value for this that's going to represent the number of milliseconds it's going to count down before it resets us. And again, the goal is pet it before that happens, and when we do, this reload register is going to be used to start it over again. The next one is the configuration register, and we talked about that a little bit, and we can look at that in detail in a second. And then we have the actual task start, which starts the watchdog. So one of the other registers I didn't highlight there, but is a key one then, is the register itself, which we're actually picking which register we're reloading. And again, you get 8 of them, but in our application we only need 1. And it turns out that that is the one that's enabled at reset. And so that's nice. We don't even have to set that. The second one is our reset value. So this is the one that starts out at a very large number at reset, and what we want to do is set it down to the value that we want it to actually count down from. And then this is the config register. So in the config register, we see the reset value has a 1 in the least significant bit. It says here that 1 means that it will keep the watchdog running while the CPU is sleeping, so that's good to know. And then the other one, which is set to 0, says that if it's 0, that it will pause the watchdog while the CPU is halted by the debugger. That's also good. So they've really, for configuration, this is optional, but they've actually picked the perfect values that I think I would typically want to use. So we don't have to set them. And then finally, the task start register, which is that offset 0, is so it's at reset, it's all zeros. It's a write-only register, and once you write to it, you write a value of 1 here, and as soon as you do that, you have initiated the watchdog. From what I can tell, looking at the data sheets, it doesn't look like there's any way to turn it off once you've started it. So once you start the watchdog, it's going to start running, and you need to keep petting it until you're going to get reset. And then one of the things before we jump into the code is I did want to just look at how we're actually reading and writing register values in C. So the way we do this is first we want to define a nice name for the particular memory location. So this was the base location where the watchdog timer is going to be set at. And this, by writing a 1 to it, was how we actually started the watchdog. And so I'm just using this as an example here, but the way you read this is, here's the address, that's what this is. As far as pre-processing is concerned of the compiler, it's going to replace all of these things that are pound defines with the actual value. So it's as though this 4001.0000 is already written right here. And then what it's telling the compiler is that, by the way, this is pointing, which is here, to an unsigned 32-bit integer. So this value points to an unsigned 32-bit integer, and then if I put a pointer here, I'm now dereferencing it. So now I'm saying whatever gets assigned here, I want you to actually write it not to this, but to what this is pointing to. So this is how we set a register. And then the reverse is reading. So here we have a status register. The status register value is here. We're telling it that, by the way, this value points to an unsigned integer that's 32 bits wide. And then, by the way, dereference it. So basically go to where it's pointing to, which would be the register itself, and put it into status. So with that, let's jump into the code and fire up a watchdog. And it really is remarkably simple. So first what I'm going to do is show you how I am invoking basically a new library that I've created. It's a new C++ class, and it's called WCL Watchdog. And the code is over here, and we'll take a look at that in a second. But I want to come down and look at a couple other things that I've added. So first of all, we've defined a new watchdog timeout, and this is in milliseconds. And so we've defined it to be basically 5 seconds before we time out. And then we've actually declared the variable WD for Watchdog, and it is of the type of this class, WCL Watchdog. But one of the things I like about this is that I haven't actually initialized it or started it yet. Again, if you look at how Particle does the Watchdog through software, once you declare it, it's actually initiated. And the tough part about that is when you come down into setup, you'll see here in setup, we initialize some GPIO. Those things go pretty quickly. But then we actually start bringing up the mesh network, and then we start bringing up the Wi-Fi, and then we start attaching ourselves to the Particle cloud, and then we sort of clear the display, we launch some independent threads and so forth. And doing all of that, especially when you're dealing with the radios here, those may take some time. And there definitely is some variability. For example, when you're jumping on Wi-Fi, sometimes it jumps on right away, sometimes it may take 20 or 30 seconds. I really don't want my Watchdog timer running at this point because I feel like I can get in a situation where the Watchdog timer keeps resetting me because it's taking too long to get onto Wi-Fi. So we do wait until we get down to the end of the setup, and at that point I do an initialize of the Watchdog, and I give it a timeout, and when we go look at the code, we'll see that that actually starts the Watchdog, okay? Then we have a Boolean that says keep petting Watchdog. Now this would not be in our normal production code, but this is what I'm putting in to test. So basically what I'm saying is that if this Boolean is true, we're going to keep petting the Watchdog constantly, and therefore we shouldn't see a reset. However, if we set this to false, we will stop petting the Watchdog permanently, at which point within 5 seconds of doing that, we should see the system reset. So the way we do that in loop is we have a digital I/O pin that's coming from the display, which I'll show when I do the demo of this. Normally that pin is high, but when you push down on the button, it will go low momentarily, and we'll catch that. When that goes low, we'll set this variable to false, and we will also set a LED that we have set up that normally is high. That LED will go low. So that will indicate to us visually that we have recognized that we're no longer petting the Watchdog. And then of course in here, we're saying if we're supposed to keep petting it, we do. So we do wd.pet. If we're not supposed to do this or false, this will not run. And of course, if this keeps running for 5 seconds and we haven't hit the pet, then it should trigger the reset. So let's look at the library itself. So what I've done here is a couple of these things that we've talked about before with our classes. We want to include application.h, and we want to do this pragma once. And then I've defined all of the pound defines that go with the various registers that we find in this data sheet here. So if we go through the data sheet, we see all the various registers that are associated with the Watchdog timer. And then we didn't talk about this in the slides, but this is the reload value. So what I think is very interesting about this is that it's not enough to just set a register to a 1 or a 0 or whatever every 5 seconds, if that's what your timer is set for. You actually have to set it to a specific value, and that this is a value that they've picked. It's not changeable, and it's what the hardware is looking for. And I'm guessing that what this is allowing for is the case where somehow the software randomly does keep hitting the register, but it's lost its mind, it's not doing it with the same values, and it wants to catch that. So at this point, it has to actually be that value. And then some of the methods that I've sort of made public here, one is the initialize, of course, and you're going to give it the time in milliseconds. The pet, which is actually petting the Watchdog, causing it to go back to the beginning every time. Another one is the isEnabled function, and that will tell us if the Watchdog has really been turned on or not. And then a couple of configuration ones, which we won't go through in this video. Again, these are the ones that are hitting the configuration register to determine whether we should keep the Watchdog running when we're sleeping, or should we keep the Watchdog running even though we've hit a breakpoint, etc. And those actually turn out to be the defaults are what I want anyway. So if we look into the implementation of this, of course, we include the H file, and then here we have the initialize function. And the initialize function is going to do three things. First, it's going to set one of the registers. So here, this particular register is the register of the 8. It's the first register that we're going to keep reloading. And actually, in the documentation, it shows that this is the default. So instead of really being 3 steps, it really is only 2 steps. So we don't need to do that, but doing it doesn't hurt, so I'm going to leave it. The second one is the reload value register. So this is where we take the time in milliseconds and we multiply by the clock frequency in kilohertz, and we end up with a value that's about 28,000 hex. And that will count down about, at that frequency, about every 5 seconds. So that's our reload value. That's what we want to reload every time we pet. And then finally, the register itself, which is the task register, when we set it to a 1, that's going to fire off the Watchdog timer and start it running. And then, of course, when we pet it, this register, RR0, which is the one that we said is the first one, that's the one that we're going to reload. We hit it with this reload value, which is this crazy hex number. And when we do that, then it goes back to the beginning from timing down. And then finally, the is enabled. So there is a run status register. And again, we're using our ability here to look at the dereference this address. And we're checking to see if it's equal to 1. If it is, it means that the Watchdog is running. So that gives us a visual indication. If before this is initialized, if we tried to do this, we should get a 0, otherwise we'll get a 1. So that's the code. I mean, it literally is, I mean, you could do this without a library to start with. You literally have 2 lines right here. This will fire it up, and this line is going to pet it, and you're good to go. 3 lines of code. Now, I've done it through the library process, and I want to build this up a little more so that it's reusable and I can make it, put it up to Particle and make it public. But this is remarkably easy and surprising to me for this microcontroller on how easy it is to get a hardware Watchdog timer up and running. Okay, so let's see our Watchdog in action. So what I've done here for our display that's going to go in the closet, I've just temporarily added a wire here coming from the output of our featherboard, which actually is an output that represents one of the 3 buttons here, which is the center button B, and it's going to D6 on our Argon. And the code that we've loaded, which we've already reviewed, is basically spinning and looking for that button to go low. And when it does, it's going to stop updating the Watchdog timer. So as we can see right now, we're sitting and running perfectly fine. Every time we get a measurement here, a measurement shows up here through the mesh network. And so what I'm going to do is hit this center button. And the light has gone off, which indicates that we're no longer updating the Watchdog or petting it. And sure enough, after 5 seconds, it reboots. That is exactly what we want. And we're back up and running. And it will continue to run like that until some event occurs that stops the Watchdog from being petted, which in this, in our normal instance, we wouldn't implement something like that with a button. We would actually, it would happen because there was a memory overflow or some other anomaly that we weren't anticipating, in which case the Watchdog stops being petted and we end up causing a reset to sort of get us back into health. And there we go.